Hello, everybody. So I decided to do a screencast on lesson 37 because I think second period we didn't get all the way through these notes. So you will go through and listen with the video. You can pause it at times and then click down to answer the questions in the Wiser Me worksheet. So today we're going to talk about the electron domain. Here are the objectives and the key question. Get out your notes and make sure, pause the video and get out your notes if you haven't yet. Make sure you have everything written down. So you've done this table talk question before, but think about it and enter your response in the discussion. You can respond to somebody else's or you can enter something new. Okay, so this whole lesson has to do with an introduction to the shapes of molecules. So it's really the valence electrons that influence the overall shape of a molecule because those valence electrons are the ones involved in bonding. So we often look at carbon atoms because carbon has 4 valence electrons, which means it has the place to make 4 bonds. And this shape, this tetrahedron shape, is kind of the basis of all of the shapes that we have. So it's kind of the foundational shape. And the reason why is because the electrons are always going to pair up. They're either going to be paired up as a shared bond, or they're going to be lone pairs. So this is the basic foundational shape. All of the other ones are modified versions of this one. In our activity before the break, we had the gumdrops and the marshmallows and the toothpicks, and you created the tetrahedron shape. So I know this is fuzzy. I can't get the online version of the textbook to come out clearly, but the idea is still there. So this is a pair of shared electrons, and that's what's creating the covalent bond between these two atoms. And these electrons take up space. And as a result, they push away from each other, and we get a couple of facts or a couple of results from these valence electron pairs. And this theory is called the electron domain theory. This picture here is your gumdrop and your marshmallows that you kind of created on your own for CH4. And if you have not written this down yet, go ahead and pause the video, write down the definition for the electron domain theory. Great. So when you made your model, I kept coming around and telling you that the distance between the marshmallows all needed to be the same. And eventually every group got it. So there's a couple of things to note about the electron domain theory and electron domains themselves. Pause the video and write down any information that you don't have yet. All right. So in this example and in your example with the CH4, the gumdrop, and the marshmallows, that first molecule you had to build, there are 4 spaces available on the carbon atom to attach hydrogen. So there were 4 things here. But sometimes, like with nitrogen, you can only add 3 things. So what's the other one? Those are the lone pairs. The lone pairs also affect the shape of the molecule, but I'm not sure why. A little note here about your book. It only takes into consideration bonded pairs when counting the total number of domains. So for example, this one would have 4 electron domains because there are 4 bonded pairs. However, the lone pairs still affect the shape of the molecule. So let's keep going with this example. The electron domain theory results in three main facts about all molecules. The atoms are equidistant from the central atom. That means we have atom A right here, which could be a carbon, and these could be hydrogens. But the distance between A and B is the same for all of them. One is not further away. Even though it may look like that when we draw it, they are all the same distance from the central atom. The second fact is that all the electron pairs surrounding a central atom are equidistant from each other. So this is where I had you measure the marshmallows and show that they were all the same distance from each other. And notice that it says all electron pairs. So this includes bonded pairs and lone pairs. And then the final thing, which we're not really going to get into measuring, and we're not going to do a whole lot with, but the bond angles are the same as well, which means that the angle between BAB is the same as the bond angle between this set as well. And in a tetrahedron for this one, I believe it's 109, I think your book says, 109 degrees if you were to measure it. We're not going to get into that. We're not going to measure the bond angles, but you do need to know that in the case where you have carbon surrounded by atoms, the bond angles are the same. So this tetrahedral shape is the foundational shape. And it's the foundational shape because all atoms need 8 valence electrons, or 4 pairs of electrons. In this case, carbon has 1 each to share with a hydrogen, and that will give it a total of 8. So let's consider this with our lone pair paddles. If you don't have this information, pause the video and then start it back up. All right, so the underlying shape is always the same. It's this central atom with 4 pairs of electrons. Sometimes all 4 of those pairs are bonded pairs, in which case you have something like CH4. Sometimes only 3 of them are bonded pairs, like in the case with nitrogen. That 4th pair is a lone pair. So how do you know whether it forms 4 bonds or 3 bonds, or in the case of oxygen, 2 bonds and then 2 lone pairs? Or in the case of fluorine here, 1 fluorine can only make 1 bond. This right here goes back to your periodic table. So I brought one home to share with you. So if you look here, hydrogen is up here and it's the exception, but all the other ones are going to be over here. And you'll notice that, and I guess it's backwards, but you have carbon, nitrogen, oxygen, and fluorine. So you have group 4A, okay, so it can make 4 bonded pairs. Group 3A can make 3 bonded pairs, 2 bonded pairs, and 1 bonded pair. So if it can make 1 bonded pair, that's true for everything in this group, and everything in this group, and everything in this group. So if you look at your periodic table, you'll notice that carbon and everything in group 4A can make 4 bonded pairs, and it will always have a tetrahedral shape if there are 4, like H4, if there are 4 additional atoms. Nitrogen can only make 3 bonds, so at most it can have 3 bonded pairs. And it shows that here with the 3 hydrogens. Oxygen can only have 2 bonded pairs, so you see that with H2. The others that make up the shape are these lone pairs. Now, most models that you'll see, and the ones that we'll continue to look at and use, don't include the lone pairs, so they look like this. This is a tetrahedral shape, and I'll have to move my mouse in a minute. This is a pyramidal shape, bent shape, a linear shape, and then this is a point. This represents the noble gases. They already have 8 valence electrons, so when we pair those up, it's completely covered with lone pairs, and it doesn't have an available electron to make a bonded pair. All right, here's the key question answered. Rewind and play back this video as you answer the questions in the Wiser Me worksheet. And that's it. Email me with questions.